We have been looking at the derivation of the Schwab-Zeldovich formulation leading up to formation of these coupling terms of a linear operator working on both the energy and the continuity. So the steps that we have followed so far is to have the overall continuity taken into account in the simplified energy equation, where we are having the relevant terms based on the assumptions that we have made, and then we add this term which is having a essentially amounting to 0 to the energy equation, so that we can now group these two terms together, and we now have a v plus vk. So this is actually amounting to the species velocity. So this is sort of like saying, recall, this is actually the mixture averaged convection of enthalpy of the mixture averaged enthalpy. This is actually the enthalpy convection due to diffusion. So if you now try to put these two together, this would actually be like the species velocity convecting the species enthalpy, right. So effectively we are having like a species specific convection of enthalpy grouping together. That's actually happening at the from the across the surface of a control volume. This is conduction happening across the surface of a control volume. So obviously we are having like a divergence of both equal to 0, because when you now have surface effects, the Gauss's divergence theorem shows up this divergence here. So you can clearly see the physics of the manipulation also that's going on. But here what we then do is, well, if you now have something like a species specific enthalpy convection, can I now use the species specific mass consumption, mass convection, right, that's equal to the, so since if you now look at this as like a species velocity, small vk vector, then the diffusion is embedded in it, so we don't have to worry about diffusion explicitly. So then it would be like species convection equal to reaction, okay, or the production, or should have actually had a wk here. Right. So of course you don't have the unsteady term because you assume steady state, so whatever is convecting in and out should be based on how much is being produced or consumed inside the control volume. That's how the species conservation looks like, which is now possible for us to plug this into this, okay, and then we do the expansion of the enthalpy, the species enthalpy, and say this is like standard heat of formation plus the sensible enthalpy. You now plug that in there, and what you will find is, for example, for that term with the standard heat of formation alone, you now try to use this equal to wk. If you did that, then you would get this to be taken to the right hand side with a negative sign, and for the remaining you now keep it as it is, but then notice that this is going to be mixture averaged anyway, therefore you could go ahead and sum over all CPKs, and then you get like a CP, right. So here CP is equal to sigma equals 1 to n yk CPK, right. So that's what is being used over here, but you can't do that here because you have a capital Vk that is weighting it, so you have to have a yk vk CPK within this integral, so you can't get this yk alone here and then have the summation, the vk is interfering there. And then we had the k gradient t coming from here as it is, and I told you how we got this right hand side. Now what I would like to point out, which I did also previously, is this is the chemical heat release rate term that has now been identified explicitly for you. What I would like to think, what we should like to think about is, so how does this really work? Delta H of k naught actually means the standard heat of formation of species k, right. So that's going to be in terms of something like joules per kg or joules per kilogram of species k, and Wk is actually the net rate of production or consumption of species k in terms of something like kilogram per meter cube per second, right. And if you now add up this product over all of the species, you're now going to get the net heat release that's been produced out of this chemical reaction. There is an alternative way of doing this. So this is actually per species, right. So you now take heat release per species and then add up across species. Of course in the Schwab-Zeldovich formulation, the I guess the ninth assumption is assuming a single step chemical reaction. But what if you had multi-step chemical reactions, right. So we know that for a chemical reaction which is not necessarily a formation reaction, any chemical reaction, you will have a heat of reaction, let us say standard heat of reaction. So if you now had a standard heat of reaction for one reaction, but you now are looking at like a multi-step reaction scheme, each of these reactions having a standard heat of reaction associated with it, which could be endothermic or exothermic, right. So if you now have all these reactions happen and each of these reactions has a reaction rate associated with it, right, which is not specific to any particular species that's participating in the chemical reaction in those reactions. So on the one hand you have a heat of reaction, on the other hand you have a reaction rate. So from there you should be able to find out what is the rate at which heat is released in a particular reaction, and then you can now look at all the reactions together and find out what is the heat released, the net heat that is released per unit time, that is the heat release rate per unit time for all the reactions happening. So there you sum over reactions. So one of the exercises that you would like to work out is it possible for you to show that the heat released from the chemical reactions on the whole is the same regardless of whether you actually summed over the species and their heats of formation or summed over the reactions and their reaction rates, right. So that is something that we will not really pursue here because we make an assumption about single step chemical reactions, okay. But that is not going to actually stop us from writing another expression for multi-step chemical reactions in terms of reaction rates and heats of reactions as opposed to heats of formation of species that we are doing here. So where are we actually going to use the single step reaction assumption is yet to be seen. We have not really utilized it yet, okay. So that is one thing that I wanted to point out. So while we have now dealt with this term, there are three terms that we want to now deal with on the left hand side, and let me just number them as 1, 2, 3 so that we will actually try to work on some of these terms identified by the numbers. So so now let us for example take term 3, right. So if you now take term 3, that's like K grad T, that's the simplest looking term in all of this. So let's now take this, and then here what I'm going to do is I'm going to write K and then multiply and divide by rho Cp d with a rho d put over there and a Cp put over here, and then write the grad T. Hey, that looks like a lot of cosmetics that has been done around without any effect, but what's in here now? What do we have? So this is our Lewis number, right. This is our Lewis number, that's equal to K over rho Cp d, and we have assumed it to be 1, right, and therefore so this is assumed, therefore this is now nothing but rho d Cp grad T. Alright, so that is what you are going to get for the third term. So effectively what you are basically saying is the conduction is going to happen pretty much based on the diffusivity because the Lewis number is equal to 1. Yeah. Okay. Now the second term is a little bit more complicated to deal with. So term 3, alright. So the term 3 is rho sigma k equals 1 to n yk capital Vk vector integral t superscript naught to t Cpk dt, all right. Now we will have to actually show why what this amounts to, and so I'm going to try to show that for you. So this is, I'm going to show that this is like minus rho d sigma k equals 1 to n grad yk integral t naught to t Cp k dt. This is actually coming from, so I'll open parentheses here, multi-component diffusion equation, right. Multi-component diffusion equation simply boils down to d gradient xk equals xk sigma j equals 1 to n xj vj vector minus xk vk vector k equals 1 to n. This is to say, in the multi-component diffusion equation, only the first term on the right hand side survives, and all the other terms are all the other terms vanish because of the assumptions that we have made exclusively to get rid of them. And we also have made the assumptions that all the binary diffusion coefficients are equal to d. So you just have to unwrap the left hand side and the right hand side together in the multi-component diffusion equation to get this. Now you can further, so what you can actually do here is, now we are not really interested in having xk, we are interested in having yk, that is what we are dealing with, right. So one way of actually trying to get rid of this is divide by xk and multiply by yk, right. So if you do that, then what you will find is you have a grad xk by xk, right, that gives you something like a grad natural logarithm xk, right. So you get into those kinds of things. So what I would say is multiply, I'm going to skip steps here, multiply by yk by xk and sigma k equals 1 to n, right. That means you add over, you should, okay, so you now get a d gradient natural logarithm xk minus sigma j equals 1 to n yj gradient natural logarithm yj should be xj, I guess, xj equal to minus vk, right, k equals 1 to n. Now so you can show this, okay, so show as in, like, you know, try to do this, and then you can further simplify this. If you now try to write it out for all the species, you can say further show vk vector is equal to simply minus d gradient natural logarithm yk, k equals 1 to n, right. This is actually retrieving Fick's law. So the way we have actually made the assumption that dij's will be equal to d, and also getting rid of all the other terms except the first term on the left hand side of the multi-component diffusion equation, should essentially amount to being able to retrieve Fick's law for a multi-component system, right. So if you now say Vk is equal to minus d natural gradient of natural logarithm of yk, this amounts to saying gradient yk divided by yk. So this yk can actually go over here to the left hand side, and then you can now see how this yk vk can be written as minus d gradient yk. So we also had a rho, so the negative sign and the rho will go there, then sigma k equals 1 to n gradient yk integral t naught to t cpd. So you can so use this above. Okay, so that closes this parenthesis. Then let us now consider, but gradient of t naught to t cp dt, right. The reason why we want to do this is we now find that gradient yk shows up here, right, and then you now have a cp integral cp dt. Let's look at what we have over there. We have a divergence of rho v cp dt, right, and I'm sorry, no, not that. You see here, you now see rho d cp grad t. Okay, so there the gradient is actually on the temperature, and here the gradient is on the yk. So is it possible for us to see if we can combine these? So if you now consider this particular term out of the blue, seemingly out of the blue, okay, we just consider this term, then gradient let me we can now write this as gradient of sigma k equals 1 to n yk integral t naught to t cpk dt. Not a problem, simply writing what cp is starting from here. Okay. It's only cp that needs to be integrated with respect to temperature, not yk, so you can pull the yk out of the integral, but it has to be within the summation. So let's now try to get the gradient inside the summation and see what happens. So this is k equals 1 to n gradient yk, alright, integral t naught to t cpk dt plus sigma k equals 1 to n yk gradient integral t naught to t cpk dt, right. So this is equal to sigma k equals 1 to n gradient yk integral t naught to t cpk dt, and then we now have to see what's going on here. T is a variable, right. So we are looking at actually taking a gradient of temperature. This has always been in our minds, alright. We always found that temperature is actually the variable sitting on top of this integral. So if you want to look at any gradient that needs to be taken, derivative that needs to be taken with respect to temperature, what do we need to do? We will have to apply Leibniz rule, because Leibniz rule is where you now are looking at derivative of an integral whose limits or functions of what you are going to take the differentiation with respect to. Okay, so that's where the problem is, and so that is going to yield for us plus sigma k equals 1 to n yk cp k of t grad t. The way it works is Leibniz rule. So this is actually coming out of Leibniz rule. The way it works is you evaluate the integrand at the limits and then multiply that by the gradient of the limits or the differentiation of the limits. So in this case T naught is a constant, so the second term which is having a gradient of T naught is going to vanish, so you don't have to worry about evaluating the integrand at T naught. So the only term that's going to actually and then of course what you then can do is you will also have a another term which is like an integral of gradient of CPK, okay. So that is not going to contribute. So what is going to contribute in these three terms from Leibniz rule is only that term where the gradient of T is there with the Cp evaluated as the T. That's how it goes. In fact in my notes I'm a little bit more particular about pointing out that you can say this is actually this is T prime dt prime, okay. So where we are now saying T prime is like a dummy variable of integration, whereas here we are evaluating the temperature that is going to be there as an unknown, okay. So if you now are okay with this, then what happens is we now get sigma k equals 1 to n gradient yk integral T naught to T Cpk dt plus grad T doesn't depend on species, so that can be pulled out of the summation and all you have is sigma yk Cpk, which is simply Cp, right. So this is like Cpk Cp grad T, right. So what are we trying to do? We are now trying to look for this term in here, okay. So from the third term we got this by applying the multi-component diffusion equation reducing to Fick's law to get this term, right, and this term can be identified here as what we started out with minus this, okay. Therefore sigma k equals 1 to n gradient yk integral T naught to T Cpk dt. Let's also do this a little bit better. If you want to now look at this as a negative sign with a negative sign, therefore minus rho d, right, then what happens? You now throw in a minus rho d over here, so you now have a minus rho d gradient integral T naught to T Cp dt, that's here, and then this goes to the left hand side with a negative sign, but you have multiplied by a minus rho d, so you get a plus rho d Cp grad T, right. Good. Then what happens? Try to put all these things together, right. So we have the first term as it is, just keep the first term as it is, rho v integral T naught to T Cp dt, okay. The second term has been the one is the one that's been giving us a little bit of a problem, and that's now looking like effectively two terms, okay. So that is minus rho d grad integral T naught to T Cp dt plus rho d Cp grad T, okay. The third term is coming with a negative sign k grad T, which is also written as rho d Cp grad T. So if you now have this subtracted from the second term, you can clearly see that this gets cancelled with this right away, okay, and this appears with a negative sign along with the first term, and of course the last term on the right hand side remains as it is. So we now can assemble all these different pieces of the energy equation. So therefore the energy equation becomes divergence of rho v vector integral T naught to T Cp dt. That is exactly the first term. We need to borrow only this term for the second term, the other one is going to get cancelled with the third term. So we have minus rho d gradient integral T naught to T Cp dt equal to minus sigma k equals 1 to n. Whatever we had on the left hand right hand side there we will just copy here. So delta h of k naught wk. Alright. What is this like? So the last 5 minutes, 5-10 minutes we have gone through like huh, but what have we got finally? Is it something that we can think about? Yeah, this is the mixture average velocity, right? This is the sensible enthalpy of the mixture. So this basically means this is the convection of the mixture enthalpy, alright, and this you can clearly see is divergence of gradient of something, right, with a rho d sticking in there. So that is actually the diffusion term. It's effectively coming from a combination of species convection of enthalpy and the conduction. Okay, so this is acting like the diffusion term, and of course that's a chemical reaction rate term. So we now see that there are three effects that are now coming together: convection of the mixture, diffusion, and chemical reaction. So whatever we talked about right at the beginning of the course, okay, where we are now talking about a interplay of three processes: convection, diffusion, reaction. So after all the shake up that has happened, we finally come down to only these three, right? So that's the physics that's involved in this equation. We call this the Schwab Zeldovich energy equation. Right. So we also want to work with the species equation, right? So let's get back to how the species equation looks like. Equation B. So equation B is now divergence of rho yk v plus vk equals wk. We don't like capital Vk. We don't want to look at capital Vk. In fact, what we decided here was we wanted to throw out capital Vk. That's how we got this rho d grad yk sigma, right? So that's coming from how the fixed law looks like. So we want to be able to now substitute Vk is equal to minus d grad yk divided by yk, or in other words yk Vk is equal to minus d grad yk. If you're able to now substitute it over here, right, then what happens? Divergence rho v yk plus, with the negative sign, minus d grad yk, right? That's what you're going to get. So let's try to write that out. Species equation B becomes applying the simplified form of multi-component diffusion equation, right? We simply get divergence of rho v yk minus rho d gradient yk equals wi. This is what we want to call the Schwab Zeldovich species equation, right? So here again you can see more clearly this is convection of species, this is diffusion of species, this is reaction of species, right. So in species conservation also we are having convection, diffusion, reaction, 3 terms. The other interesting thing is this is rho v times something yk in this case and minus rho d grad that thing which is yk in this case. Here we have rho v times something which is a little bit more complicated than that, integral T naught to T Cp dt and minus rho d grad the same thing which is integral T naught to T Cp dt. And what did we want? We wanted our left hand side to look like some sort of an operator that's operating upon a quantity like alpha I or alpha t. We are now beginning to think, we are now beginning to see the contours of that. Both the left hand sides of the Schwab Zeldovich energy and species equations are actually on the same operators operating upon 2 different quantities, in this case yk, the other one is integral T naught to T Cp dt, right. So we are beginning to achieve this goal. But what was our original goal? Our original goal was we wanted to have a operator script L of alpha I is equal to omega and operator script L of alpha t is equal to omega. That means we wanted the right hand sides to be the same, okay, but that's not the case. You now have a wk over here, right, and you have the wk within a summation over all k. How is that, how do we deal with this? So this is actually, this is first of all this is n equations, k equals 1 to n, right. That's one equation summing over all wk weighted by the delta h f naught k. So how do you deal with this situation? So you now try to form, so you aren't quite at the alphas yet. We have identified yk and integral T naught to T Cp dt as potential candidates for our alpha k and alpha t, but the right hand sides aren't looking good, right. So let us do something here. So for a chemical reaction, of the form sigma I equals, we can say, you can keep it k equals 1 to n nu k single prime script mk gives sigma k equals 1 to n nu k double prime script mk. That is a single step reaction, okay. So you are now beginning to start thinking about a single step reaction as opposed to a multi step reaction scheme. We may write omega equal to wi divided by cap, or should say wk equal to divided by capital wk nu k double prime minus nu k single prime k equals 1 to n. This is how we defined our omega, which is the molar rate of reaction, okay. The fact that we are now bringing in moles is because we are now dividing by the molecular weight capital Wk, right. Now this can be done obviously only for a single step reaction. If you had multi step reaction, then you had many omegas themselves. It isn't possible for you to write a single omega, right. So a single omega can be written only for a single step chemical reaction. That's where we have to bring in the single step chemical reaction assumption. And what you're essentially saying is, let me now try to look for something that's common for all wk so that I can just have that alone and pull everything else to the left hand side and keep only the omega on the right hand side. I can easily achieve that with the species conservation equation, because I have this definition that relates the WKs to the omega, the single chemical reaction rate. So if you now, so what you do, if you now were to divide your equation, your kth species conservation equation by capital WK times nu k double prime minus nu k single prime, right, the right hand side becomes omega, and then the left hand side you don't really have a yk in itself, you have a yk divided by capital WK times nu k double prime minus nu k single prime, right, that's your alpha k. So then let alpha k equal to yk divided by wk nu k double prime minus nu k single prime, right. Good. Can you also substitute wk equal to omega times capital WK nu k double prime minus nu k single prime? Okay, can we now substitute that over here? If you did that, then you are going to get this term as sigma k equals 1 to n delta hf k naught capital WK times nu k double prime minus nu k single prime times omega. Omega does not have any subscript k, therefore I can pull that out of the summation and keep it as a factor, and whatever is there in the summation, the summed up quantity, I would now try to divide that throughout. If I divided this equation throughout by that summed up quantity, leaving only the omega on the right hand side, I have only omega on the right hand side, and I am going to get omega on the right hand side for here as well. So now I am beginning to look at a alpha t. So alpha t is, originally we thought our candidate was integral t naught to t Cp dt, but now it is actually divided by sigma k equals 1 to n delta hf naught k capital WK nu k double prime minus nu k single prime. So what if I use these alphas now in the Schwab Zeldovich energy and species equations? Then we can write L of alpha equal to omega, right, where alpha equal to alpha k, k equals 1 to n gives species equation, I should say SZ species equation, and alpha equals alpha t gives SZ energy equation. So what is L for us? And here L effectively is, L of alpha is divergence of rho v vector alpha minus rho d gradient alpha, right. So that is divergence rho v alpha minus rho d gradient alpha equals omega, and this is convection, this is diffusion, this is reaction. We have pretty much achieved our goal, right. All we have to do now is to notice that this is a linear operator, so it is possible for us to now subtract one alpha from the other, and the right hand side is the same for all these equations, therefore you should get a 0 there, right. So notice L of alpha is a linear operator, okay. So the nonlinear chemical source term can be eliminated in all but one equation by subtracting that equation from all other equations, right. Then we have L of alpha 1 equal to omega and L of beta equal to 0. Okay, where beta equal to alpha t minus alpha 1, so let us call this beta t, and beta can also be equal to alpha k minus alpha 1, let us call this beta k, k equals 2 to n, right. So the betas then are what is called as the coupling terms, right. So you now have linear homogeneous n minus wait a minute, this is one equation, this is actually again n minus 1 plus 1. Originally we had n plus 1 equations, n species equations and one energy equation, right. And if you now subtract all equations, so one equation from all other equations and keep this one equation, you should still have n plus 1 equations, but n of those equations have now become linear, have become homogeneous, right. It is only one equation that continues to have the inhomogeneity. Therefore you now have you have now changed your system of equations into n linear homogeneous equations and one linear inhomogeneous equation, alright. So that's what you achieve by doing the Schwab-Zeldovich or adopting the Schwab-Zeldovich formulation. This is a good point to stop. We will start thinking about what to do with the formulation as we proceed.